Welcome back to the course on electronic packaging and manufacturing, and we will continue from where we left off last time. We were talking about semiconductors and devices and or components. Okay, so if you recall this, these are the topics that we were going to cover: conductors, insulators, and semiconductors, and extrinsic semiconductors. So these two was covered in the last lecture, and today we are going to take off from there, and we will talk about what is a p-n junction, what is a diode, and then we will end this lecture looking at the steps of how we can make or fabricate a diode. Okay. So with that, what we will do is we will go ahead to the place where we stopped last time, and this is where we were. We had discussed about n-type semiconductors, we had discussed about p-type semiconductors, and we saw that in a p-type semiconductor we have charge carriers in the form of electron holes, whereas in n-type semiconductors we have charge carriers in the form of electrons. Okay. Now, what can we do if we have a p-type semiconductor and an n-type semiconductor? What can we do? Okay. So, that brings us to the concept of what is called a p-n junction. Okay. As the name suggests, a p-n junction is a p-type semiconductor and an n-type semiconductor which are joined together, which are placed next to each other. Now, recall what happens in n-type semiconductors. You have free electrons. In p-type semiconductors you have holes which can accept electrons. Now, if you place them side by side, make a junction of a p-type and n-type together, what will happen? Very close to the junction, as we see here, this region, the one that I am circling, what happens is the free electrons and the holes, they recombine, okay, to form a region of what is called it's a neutral region. It's a region that is devoid of any free charge carriers, whether it's electrons, whether it's a hole, because the hole and the electron recombine. Okay. But however, as they recombine, what happens? If you look to the right, you have a p region which has lot of positive charge carriers. On the left, you have the n region with lot of negative charge carriers. Okay. In the middle, we have what is known as this depletion region. So, the depletion region, what happens as a result is, I am sorry, I jumped a little bit, sorry. In this depletion region, what happens over here is there is a potential difference as a result that is created. Okay. So, here you have no free charge carriers because the holes and the electrons have combined. On the left side you have free electrons, on the right side you have free holes, or not free holes, you have holes which can accept electrons. But because of this depletion layer in the middle, it forms a barrier, and the electrons from this side cannot jump to the holes on the other side, because if it has to do so, it has to go through, let me go back, it has to go through what is known as this potential barrier, which is a potential difference across the junction caused by the depletion layer. Okay. So, this is what a p-n junction is. But what can I do with this one? Okay. It is a p-n junction with a depletion layer in the middle, which has caused a potential barrier and preventing electrons from flowing from one end to the other. So, can I make it flow, or can I do something else? If I do not do anything, what happens? Okay. So, if I do not do anything and just leave it the way it is I am calling that a reverse bias. Okay. Reverse bias, nothing will happen. We have connected the two ends, but we have not given it anything. Okay. So, it's a I take my word back, it is called a zero bias. I have not biased it with anything, we have not applied any potential difference across, or external potential difference across the two ends. So, it remains the way it is. Now, let us say I do this, where what I do is I apply an external voltage or external potential difference, but I connect the positive terminal to the N side and the negative terminal to the P side. Okay. So, what will happen? What will happen is the fact that this electrons from the N side is going to be attracted away from the depletion from the junction, and same for the holes, and therefore the potential barrier will further increase. The depletion region will widen, the potential barrier will further increase, and there will be no current flow from the P side to the N side, because for current to flow, the holes have to flow from right to left and electrons from left to right, but here it is just the reverse is happening. Okay. So, this is known as reverse bias. Okay. So, in the reverse bias, what happens? There is no current flow. Clear? But however, if you apply the voltage, if you reverse the direction of the applied voltage, or in other words, you connect the positive terminal of your external voltage source to the P side and the negative terminal to the N side, then what happens? Then what happens is the holes are going to be attracted towards from the P side to the N side, and the electrons are going to be conducted from the N side to the P side. As a result, what is going to happen? As a result, what will happen is the depletion region is going to reduce further and further, and the potential, the potential difference, the potential barrier that we saw is going to reduce. Let us try to sketch that a little bit and see what happens. Okay. So, let us do this. Okay. So, I have attached the positive side to P and the negative terminal to N. So, earlier what did I have? If I had to draw the potential barrier, it was something like this. This was my depletion region. Now, what happens slowly is with time, what happens is the depletion layer also reduces in size, and the depletion layer reduces in size, and the potential barrier also reduces. Okay. And slowly we are finally going to reach a stage where it is going to be like this. Okay. So, what I am saying is, as time progresses, and when I say time, these are like minuscule, very small time steps I am talking about. Depletion region goes down, potential barrier also goes down. Okay. So, finally what happens? You reach a stage where you will have migration of electrons these electrons are darkened. So, they will migrate, and then you have holes which are going to migrate from the P side to the N side. Okay. So, that is what is shown in this figure as well. The depletion layer gets reduced. So, now if I do that, then what happens? There is a current flow from the right to left, or the P side to the N side, because which is opposite to the direction of flow of electrons and in the direction of the flow of the electron holes. Okay. So, therefore, we have now discussed what is forward bias. This is known as forward bias, and we also discussed what is reverse bias in the previous slide. So now what happens as I keep on increasing the voltage, whether it's forward or reverse, what will happen if I measure the current across this PN junction? So at the beginning what happens is, if you consider over here, at the beginning I am talking about forward bias voltage. As I increase the voltage, there is some threshold after which I start measuring the current. What is this threshold? Because this is a threshold that is required to overcome the potential barrier that was there initially. Okay. So for certain voltage range we will not be able to measure a current, but thereafter we will see an increase in the current value. Clear? And then as I keep on increasing the forward bias voltage, my current value is going to be higher and higher. But if you look at the reverse bias, what happens? The reverse bias, there is hardly, if you keep on increasing the voltage but in the opposite direction, we don't see current flow, except at very high value over here. This is known as an avalanche effect. We are not going to talk about that, but practically for all purposes you don't see any current flow in the reverse direction, except some very small leakage, intrinsic leakage currents. Okay. So that is a diode. Okay. A diode is often denoted in by this symbol over here. What it shows is, and what it means is, it allows current to flow in one direction but not in the reverse direction. It's like a valve, like a mechanical valve. A valve allows flow across an orifice in one direction but closes it in the other direction. A diode is the equivalent in the electronics world. It's a component which allows current to flow in one direction but not in the other direction. Okay. So that is a PN junction diode. There are many other types of diodes, by the way. So I have given one of the sources in the references. If you go through that, you will be able to see a lot of other types of diodes, but this is the most simple case of a PN junction diode. Okay. So this was more of a refresher. Okay, maybe probably you have already studied this as part of basic electronics, or maybe even class 12 physics, high school physics, but this was more of a recap of what we had already learned. So now that we know how a diode works, at least the PN junction diode works, let us see how we can make one. Okay, and that brings us to the world of electronic packaging and manufacturing. Especially now this is about microfabrication technique. How do I fabricate a diode? How do I make a diode? All right. So let us, before doing that, what I am going to do is I am going to talk about a technique which is known as lithography, because this is essential to understand before we go on to see the fabrication steps of a diode. Now this is something we are again going to see later when we talk about first level packaging, second level packaging, particularly motherboard fabrication. Lithography will be extensively used, but in this case, let us first talk about what is lithography. Okay. So a lithography or photolithography, as we talk about, is when you have a substrate. Okay, the substrate can be some material, some metal, some layer. Let's forget right now what it is. On top of that, you put in a material which is known as a photoresist. It's a material, these are certain materials, for example, PDMS. It's a very common photoresist material. Photoresist, what does it mean? That what it means is, as the name suggests, that in the presence of light or optical energy, particularly UV light, it undergoes certain change in properties. Okay, either it resists or gets hardened, or something else happens. Okay, we will come to that. So positive photoresist, what happens? You had a substrate, you put in a photoresist material and smear it and form a layer. Then photoresist, what happens is we have what is called a mask or an optical mask. What is an optical mask? Optical mask, what it means is just like a mask, face mask. What does it have? It is some, it is some kind of a pattern with certain holes through which, for example, a face mask, we have holes so that we can see and breathe and sometimes even talk. So similarly, a photo mask will have some openings, some maybe holes, orifices, slits, etc., through which if you shine light, the light will be able to pass through those holes or slits. Okay, so that's a mask. So this is a photo mask, for example. I am showing a 2D structure or 2D cross section. Now let us put UV rays. Okay, so where this mask material is, it is going to block the UV rays from passing through it, but where I have a cutout, then the UV rays pass through that cutout, whether it's a hole, whether it's an orifice, whether it's a slit, and then falls on this photoresist material. And as the UV rays fall on the photoresist material, it undergoes certain changes in properties, and which later can be removed. Okay. Now, what is that change in property, etc.? That depends on the photoresist material, but it is some change locally which can be used to remove or to remove that material later and not remove the rest of it which has not been subjected to the UV light. Okay. So similarly, so this is positive photoresist. Negative photoresist, on the other hand, is just the reverse. Same thing, you have a substrate, you have a photoresist which is smeared on that, then you bring a mask, you put UV rays, but here what happens is the change in properties is such that the exposed part undergoes some change which prevents it from being removed through that treatment that we are going to do later, and so we do some other kind of treatment by which we can remove the part which was not exposed to UV light. Okay. Clear? So again, the whole point of photolithography is that I am able to locally change the properties of a certain surface, so that later on, if I make that surface undergo some chemical treatment, preferentially material from those localized areas can be either removed or retained, depending on whether it was positive photoresist or a negative photoresist. Okay. All right. So with that, now let us look into, or let us look at, the steps of fabrication of a diode. So I am going to go very slow on this one so that you understand what is happening. The step A, we will start with an N-type wafer. So the substrate is an N-type semiconductor. All right. So what do I need, therefore? To make a junction, I need to have a P-type material impregnated into this N-type wafer. Okay. See, the way we were discussing before, it was a hypothetical situation. You have N-type, you have P-type, you bring them and join them together. In reality, that does not happen. How do you join them together? Okay. How do you make that junction? Okay. So in real life, to making that, fabricating that is a very complex process. Okay. So what we do is we start with an N-type wafer, and on top of that we grow a silicon dioxide layer. Okay. Once again I repeat, we start with an N-type semiconductor, and then what we do is we add a layer of silicon dioxide. So the surface of the silicon is oxidized. Okay. Then we add a layer of photoresist, as is shown in step C. Okay. So if we add a layer of photoresist, then we put mask, okay, and this is positive photoresist, where we will put this mask and then shine UV light, so that the part of the photoresist which was exposed to UV light can be removed. All right. So it undergoes a change in property, and then later on what we do is we can remove that photoresist from that from the area which was exposed to the UV light. Okay. I'll repeat once again. On the silicon, which is N type to start with, we put a layer of silicon dioxide, and on top of that we apply a photoresist. Then we undergo a positive photolithography process where we have an optical mask through which we shine UV light in step E, and as a result the exposed part undergoes some chemical change and can be removed. So, what do I have now? I have a device which is an N-type silicon still with a silicon dioxide layer, and then a layer of photoresist at certain locations. Okay. Next, what we do is we take hydrofluoric acid and use it for etching. Okay. If you use it for etching, what happens is the silicon dioxide layer will be removed, will be etched away. So, that is the step H as is shown over here. So, the silicon dioxide is removed. Okay. And next what we do is there is something called a strip resist method, or basically you strip off the photoresist that was still remaining over here. These violet or purple bands are then stripped off, and what we have now therefore is an N-type wafer still covered with a silicon dioxide layer, but at certain locations, thanks to the photoresist method followed, or the photolithography method followed by etching, chemical etching, we have certain parts of this N-type silicon which is now exposed. Okay. So, thereafter what we do is we diffuse what is called, we diffuse a p-type or boron into this. Okay. So, we diffuse boron into the N-type semiconductor. Sometimes it is in boron hydride, sometimes in the form of boron hydride, but what happens is therefore boron atoms get diffused inside into this N-type semiconductor. Okay. And therefore, what is this boron when it is diffused in the N-type semiconductor? This becomes a p-type. And then the final step which is not shown is, maybe if I say this is step K, sorry. If this is step K, I would say we still, now we will again HF etch the silicon dioxide layer. So, what am I left with? I am therefore left with my N-type semiconductor, but now with a p doped region inside, and that, my friends, is a diode. We have made a diode. This is how an actual diode looks like. It is not, rectangular p type and rectangular N type joined together. This is how a diode is made. Okay. So, once again, just let us spend a few seconds or maybe half a minute on the steps. Started with a silicon N-type silicon substrate, and then used oxidation followed by photolithography and chemical etching, and followed by diffusion of boron into it to form a p-n junction. Now, think about it. Can you do this again? Now, you have a p-n junction. Can I have another, can I have in this region, inside the p region, another n region? Yeah, why not? We will again go exactly by the same process, except the mask dimensions and mask pattern has to be different, but everything else is just the same. And instead of instead of diffusing in boron or a compound of boron, we are going to diffuse a compound of phosphorus. And what we are going to end up through that is an N followed by a P and again an N, NPN, and that is a transistor. Okay. So, this is a microfabrication technique by which we have fabricated a diode using microfabrication processes. Okay. And the same process, as I said, can be this microfabrication process is very commonly used and can be used to make a bunch of components or semiconductor components like this. Diode and transistor are just two examples. Okay. So, therefore, let us now quickly wrap up and go through what we have just discussed as part of this entire module or as part of this lecture. Remember, in the last lecture we had left off, we had introduced the concept of semiconductor, extrinsic semiconductor, and the concept of doping. In this lecture, we started off from there and talked about what is a p-n junction. Okay. And the p-n junction, by application of an external voltage, can be made to act as what is called a diode. What is a diode? It allows electric current to flow from one direction to another, but prevents it from flowing in the reverse direction. That is a diode. And the way that can be done is you take a p-n junction and you apply voltage in one direction, by which electrons will flow from the n to p and holes will go from p to n, or there will be mobility of holes from p to n. But if you change the polarity of the external voltage, then the current flow does not happen anymore. So, that is a diode, very basic diode, which is a p-n junction diode. And then what we did was we went ahead and said, okay, we understand what is a diode, now let us see how we can make one, and that introduced us to a microfabrication technique by which we started. In this example that we discussed, we started with an n-type semiconductor substrate and then we kind of impregnated a p-type or p-doped semiconductor into it, and thus formed a p-n junction. Okay. So, that kind of ends our discussion here, and in the next class what we will do is we will go straight into what is called the first level of packaging, where we are going to see how these devices with their input output can communicate with the rest of a system. So, that is first level packaging, we are going to talk about that. Okay. So, what we discussed, the references for the materials that we have discussed so far, again our two textbooks, Packaging of Electronic Systems by Daly and Fundamentals of Microsystems Packaging by Thumala. And then also this is a very good resource, electronicstutorials.ws. Okay. Here, if you want to just go through the fundamentals and brush up some of your basic electronics, this is a very good resource. There is another website where I showed a picture from there, all about circuits. That is also a very good website, a little bit crowded and therefore a little bit, at least I thought, a little harder to navigate through, but still a wealth of information available over there. Okay. So, if you want to brush up your basic electronics, I think these are two very good resources that you can go to. And with that, thank you very much for your attention, and what we will do is in the next class we are going to go straight into the first level packaging of electronic components. Okay. Thank you very much. Have a very good day.